Hi class, this is Dylan Blair. It's kind of a bummer. I just barely got done recording this lecture and for some reason the recording timed out, so I am recording it again. So here we go for take two. This week we are covering chapter 8, the beginning of chapter 8. I decided to get rid of 8.3 because I figured with only having Wednesday and Friday, I probably would have only been able to get through 8.1 and 8.2. So 8.3 is pushed back to next week. Chapter 8 is the concept of using polar coordinates for different ideas. And polar coordinates is just a different way of expressing something in a different coordinate system. So we can express functions in different coordinate systems. We can express points in different coordinate systems. And the coordinate system that we're typically used to using, you may not know the name of it, but it is called the Cartesian coordinate system or a rectangular coordinate system. So you're thinking about your x and y. So with these Cartesian coordinate systems, when you have some x, let's say x was negative, so you have some x and say x was negative, you go to the left, and then let's say y was positive, let's say we went up by like 3, then we can get to some point that way. Okay, note the order does not matter. We could have went up and then left, and we end up getting to that same point. Note that rectangular coordinate system kind of makes a little bit of sense because we can see we just drew a rectangle, right? So now what we're going to learn is how we can express a point in polar coordinates. So we're basically thinking about how can we extend inward and outward a radii and then rotate around positively or negatively, so counterclockwise or clockwise, in order to express a common point. Okay. And then we're going to extend this topic into polar equations. So once we actually have these tools to be able to use for converting between polar coordinates and Cartesian coordinates and back and forth, then we're going to use these tools in order to actually convert a Cartesian equation. So y is equal to x squared plus 2x, or y is equal to sine of x, right? X is your Cartesian input, y is your Cartesian output. Then we're going to learn how we can convert these Cartesian equations to polar equations, and vice versa. If we have a polar equation, how can we convert it to a Cartesian equation? For this week, you'll have 8.1 and 8.2 to read from the textbook. Please read the textbook. I'm making sure that I do not pull examples from the readings, so that that component will not be redundant for you guys. So you'll have my lecture videos to look over, you'll have the textbook to look over, and you'll also have those additional lecture videos that I'm also making sure not to pull examples from those as well, so that you guys have an abundant amount of resources during these times. Okay. A few reminders: Chapter 7 is due this Thursday at midnight, so that's March 19th. 8.1 and 8.2 will be due a week from now, so next Thursday, March 26th. And then again, I think this is like the fourth time of me reminding you guys that spring break take-home quiz is due this Wednesday, so it's likely tonight for many of you that are watching these lecture videos right now, at midnight, so March 18th. And then quiz 8, don't think of this as two quizzes in the same week. Remember, quiz 7 was before we left on spring break and we just never returned from spring break. So quiz 8 is due this Friday at midnight, March 20th. And as a reminder, this quiz will start this following this technique or this method, but I will release the quizzes at Friday morning right before office hours. And then that will be due via Gradescope at midnight. Okay, and again, to rehash Gradescope, you get the PDF from Canvas so that you can print or use or copy it over onto paper, the quiz onto paper, or you can transition the quiz onto your tablet, and then you complete the quiz, then you scan the quiz into your computer, and then you upload it onto Gradescope. Okay. But either way, we do need to finish up a few more things for chapter 7. It's the story problems. That's why chapter 7 was extended until Thursday, because there's a small amount of the problems that you still need to be able to do. And it's more so just that you guys need to know the terminology. It's you guys know how to do the problems. It's just you need to know how to actually set up these problems using this terminology. So first off, when we're talking about grade, it's just some terminology that we can actually see an example down here, and these examples will be covered in will be solved in a separate lecture video. But either way, what we can say is we can say a mountain road has a 7.5% grade. That's saying that it has a grade incline, okay? And what this grade is it's a ratio of height to length, okay? So if we think about this, our height is over here and our length is over here, and what we truly want in trigonometry is this angle, right? So what we want is we want to take the tangent alpha of the height over the length, that ratio, okay? Well, that height over the length ends up being that grade, okay? But that grade is given to you in a percentage, okay? So you need to convert the percentage into a decimal, into a real number, and then you solve for alpha by doing inverse trigonometry in order to actually get that angle, okay? Now remember, when you're converting a percentage, so say you had like 75%, remember that's equivalent to 0.75 in decimal format, which is the same thing as taking 75 divided by 100. So that's all that A divided by 100 is. Okay, then a few more terminology on these story problems. Bearings, okay, so when you're saying something like north bearing some degree east, all that's saying is that we're starting north, so that's our initial side length, and then we're rotating east. So we're starting here, and then we're rotating east by some specified angle, which is alpha. Similarly, for north bearing west, so west would be over here, north would be right here. We would start north and then bear west by some angle. Okay. Similarly for south, we'll just do one of these souths. We can start south and bear east. So we can start at our initial side and then rotate towards the east by some angle, alpha. Okay. And then you can south bear west by some angle. Okay. As I said, the examples will be done in a separate lecture video. One thing too, so as I've mentioned, there are going to be additional like assignments. They're like, I can't remember if I have the points going towards assignments or quizzes. It doesn't really matter. They're a small amount of points just to make sure you guys are watching these videos. But this week's key phrase is Dexter Morgan. It's from the Netflix TV show. Actually, I don't think it's Netflix's show, but either way, it's on Netflix. If you guys haven't seen it, I highly suggest it. It's a wonderful show. Definitely in my top 3. Either way, Dexter Morgan is what you will enter into the quiz or the assignment on Canvas in order to get the points for this week. Okay, let's move on to chapter 8 finally. Okay, so now polar coordinates. So as I said, we can start with some Cartesian points. So say that we're going to the left by 2 square roots of 3. So it'd be a negative 2 square roots of 3. And then we're going up by 2. Let's make that actually look like a 2. So as I said before, we can go left and then up. We can also go up and then left. Doesn't really matter. We end up getting to this point the exact same way. Okay. Now, in polar coordinates, we've already said that this Cartesian coordinate is x comma y is equal to this negative 2 square roots of 3 comma 2. So the x coordinate is negative 2 square roots of 3 and the y coordinate is 2. And in a few slides, we'll actually talk about how we can find these r's and thetas. I'm sure you guys could probably find them on your own anyway. But what this one ends up being is 4 5 pi 6. But we're just going to talk about this right now. We'll talk about how we find it in a future slide. So what we're saying is, you notice we already have these like dashed out circles. We're saying that we're extending out by a radius of 4, so all the way out until we get to here. So this radius is circle 4, and then we rotate around by 5 pi 6. And then this point ends up being equivalent to the point over here. Okay, so it's two different ways to express the exact same point, just we're viewing it differently. One way we viewed it by moving rectangularly, and another way we viewed it by rotating and extending in order to get there. Okay, so Cartesian and rectangular coordinates, we're moving left and right and up and down in order to get to a point. Polar coordinates, we're extending out and in and rotating counterclockwise and clockwise to get there. Now note, this in is kind of a hairy term. So that's what we're going to talk about in the next slide. We're not going to really extend or talk too much about counterclockwise and clockwise because we've been talking about that and we're very aware of counterclockwise means that we have a positive rotation, clockwise means that we're rotating negatively, right? But extending out and in is just kind of an interesting concept that gets a lot of people kind of caught up. So we're going to talk about this in more of an abstract way, and you'll see it in examples as well, but I do want to kind of explain it to you guys first before we get into examples. So let's consider that we just have some positive theta. Okay, and let's first consider on this left-hand graph that we have a positive radius. Okay, so that means that we extend out by some positive radius, say it's somewhere right here, and then we rotate by some positive theta in order to get to this point. Okay, and so that's how we can get to this point right there. Okay, now note we have infinitely many ways that we can express this point P. We can, for a positive radius, we can rotate around positive theta. We can have this positive radius, and we can rotate around this positive theta and then another revolution, right? We could extend out and rotate around an entire more revolution. We can rotate around 2 revolutions, 3 revolutions, which is just adding some multiple of 2 pi, and we can also subtract some multiple of 2 pi. And so it's that positive theta plus 2k pi. And that's that infinite term that pops up. Okay. But then let's talk about negative radii. Okay. So we actually need a different angle that corresponds to these negative radii, because we can kind of think about that we can always rotate and then extend, but when we rotate, we'd just be like rotating on this dot. So just kind of think about like a very small rotation, okay? But we know that we want to express this equivalent point P over here. And what we want to do is we want to rotate all the way around to the opposite side of P. Okay, see how we rotated all the way around to the opposite side of P? We'll call this theta prime. We'll call it a positive theta prime. And then extend backwards, so inwards. So before, over here, we were rotating up. Let's erase this guy. We were rotating up by theta and then extending out in the same direction that we rotated. Now we're rotating inwards in the opposite direction that we rotated. Okay, and then we can end up getting to that exact same point P. Okay. So now we can say, well, we could extend out negatively and rotate out some positive theta prime, which we don't know what theta prime is yet, but we'll talk about that in a second. And we can also extend out negatively and rotate some theta prime plus 2k pi. So some multiple of 2 pi, whether it's positive or negative. Okay? And we get another infinite set of solutions. And note that this is equivalent to this. They're both the exact same. We get that exact same point P. Okay? But that theta prime, we need to know how that actually relates to this theta right here. Well, we notice that they're just on a line from each other. So we could start at this theta rotation and rotate all the way around until we get over here, and we just rotated by pi in order to get there. So we could say that theta prime is equal to theta plus pi. Okay? And then we're able to capture both possible solutions or both representations of all of these. Okay? Now, we lastly just want to talk about converting between each coordinate systems. Converting from polar to Cartesian is actually very straightforward. So I'm just kind of going to give you guys the tools and explain to you like where they come from. But let's talk about that first example that we started with. Okay, so we had that negative 2 square roots of 3 and 2. So we went to the left by 2 square roots of 3 and up by 2. Well, that inherently drew this triangle for us, right? It's this right triangle. And we have some angle theta. Well, we have 2 is the height of this triangle, and 2 square roots of 3 is the length of this triangle. So we can use Pythagorean theorem in order to solve for r, the radius, or the hypotenuse. When we do so, we can solve to see that r is equal to 4. But we know when we take the square root, we also get this negative component that's a possibility. And we'll talk about that in a second. Okay. But let's first just continue on with the r is equal to 4. And then we can always say, well, tangent is going to be opposite over adjacent, right? Tangent of theta is equal to opposite over adjacent, which we can think of that being our TOA, right? So TOA. And that 2 over negative 2 square roots of 3 can simplify down to negative 1 over square root of 3, which is the same thing as negative 1/2 over square root of 3 over 2. Okay. Now we just have to decide where that negative goes, whether it's in the top, in the numerator, or the denominator. Well, let's look at this a little bit. So if it were in the denominator, we would be going upward because the numerator is positive, and that's our sign value. So it would be going up by 1/2 and to the left by square roots of 3 over 2. Well, that ends up being 5 pi 6. Okay. Well, if we went the opposite direction, we said that we were going down by 1/2 and to the right by square roots of 3 over 2, then we'd end up on this line again, right? But we know in order to get that point, we want this one, right? Because that's this point, okay? So we want to rotate up by 5 pi over 6. And we know that we can get that infinitely many solutions. We have this 5 pi 6 plus 2k pi. Right? But note that we can still talk about this 11 pi 6 plus 2k pi in a second. Okay, so let's first talk about the 5 pi 6 and the positive radius first. So we can say that that Cartesian coordinate is equivalent to extending out by 4 and rotating around by 5 pi 6, which we had talked about in that first slide on 8.1. But we have infinitely many solutions. So we could also say 4 and 5 pi 6 plus 2 pi, which is the same thing as, let's see, that is 17 pi 6. And so that would be when k is equal to 1. We could always take 4 and then take 5 pi 6 minus 2 pi, which is going to be negative 7 pi 6. So we're plugging in a k is equal to negative 1. And we can keep on doing this game over and over and over again. Okay. However, we can even rotate negatively, or not rotate, extend negatively. We can extend negatively and then rotate this other rotation. So we could take negative 4 and rotate by 11 pi 6. Well, that 11 pi 6 was this rotation. Right? So if we rotated to that 11 pi 6, but then went backwards, so we went backwards in our extension, we end up back at that same point again, which is still equivalent, okay? Which is our goal. We want equivalent representations. And we could always take -4 and 11 pi 6, and let's take minus 2 pi, which would be negative pi 6. So that bk is equal to -1, and so on and so forth. And so that would be right there. And then we extend inward. Okay. And so what this means is that this Cartesian coordinate is equivalent to this polar coordinate, or this polar coordinate, or this polar coordinate, or one of these polar coordinates, or this one, or this one, or one of these, and infinitely many options, okay? But Cartesian-wise, this is our only option, okay? Now, there is a typo in the notes. We can basically summarize everything. We can say the equations that we need for converting Cartesian to polar, not polar to Cartesian, but Cartesian to polar. We need Pythagorean theorem, and we also need tangent is equal to y over x. So if you know x and y, you literally can just plug those in right there. But x cannot be 0, or else you can't find theta. Okay. If x is 0, then there's no theta. Okay, you'll kind of see that in your examples when you guys are working through examples in your homework. And then polar coordinates, this is not one that we necessarily went through. You'll see it in some examples in future videos that I put out. Or not future videos, in other videos that are corresponding to this. But just note, this is just cosine of theta is equal to x over r. Well, r is your hypotenuse, and x is your adjacent length, so ca TOA. Cosine is equal to adjacent over hypotenuse. So it's the exact same thing that we've been dealing with all semester long. And sine of theta is equal to y over r, opposite over hypotenuse. Okay, so it doesn't really change much. Either way, thanks for listening. Make sure you fill out Dexter Morgan for your answer to the assignment, and be sure to watch the other videos for the examples. I'll see you guys over there.